Hi, welcome to section 10.3, which is on space figures. So space figures, it sounds kind of weird. It doesn't mean anything. It's not related to outer space, but it basically just means figures, shapes that are three-dimensional. So in the past section, we talked about shapes that were flat, so 2D, like drawn on a piece of paper, like a polygon. And now we're going to talk about 3D figures like cubes and cylinders and those types of shapes. So we're going to start by talking about planes. And planes, it's kind of an abstract concept. It's really hard to wrap your head around because the definition of a plane, and we talked about it in 10.1, is just an infinitely large flat surface that has no thickness. And it's hard to kind of think about why we would even need to know about that or where or how that would apply to our everyday life, because there's not really anything tangible we can think of as an example that would be infinitely large. Now we can think of planes or parts of our world that are part of planes. So for example, like the floor is a part of a plane. I mean, I say part of because the floor only has a finite space to it, like the floor that you're sitting on or standing on right now. Or the ceiling or the walls of a room. And so the reason we're talking about planes and the reason you need to kind of understand what they mean is because, when you're teaching elementary school students, you'll be talking a lot about 3D figures, like, for instance, like a prism. And when you have a prism, take a prism that looks like, so it'd be like a prism. So think like, a tissue box. A prism is made up of planes, and so it's important to be able to reference, okay, I'm talking about the plane that's in the front or the plane that's in the side, and so it helps us kind of refer to parts of these space figures. So there's a couple of different types of planes. So I want to back up, and actually it's down here. I'm going to do this first. Let's talk about lines first, and then we'll come back to planes. So when we're looking at lines in 2D, and we've kind of talked about this before in 10.1, there's two different options. So they can either be parallel or they're going to intersect. So those are the only options for how two lines can interact with each other. So here we could call this line L and line M, and we say L is parallel to M. Or we could have two lines, maybe these two lines, and we could still name them if you want to. We could still call them L and M or something else. They don't have to be L and M, and they could intersect. So there aren't any other possibilities for those lines. With planes, we have a similar type of scenario. So with planes, you can have parallel planes. So those would be planes that don't touch. And so when we're thinking about like this, we'll call it a tissue box, the top of the tissue box would be parallel to the bottom of the tissue box because those planes do not touch each other. And then we could also have planes that intersect. So just like lines in 2D, we could have planes that intersect each other. And when planes intersect, they intersect at what we call a dihedral angle. So it's just a fancy name for the angle at which planes intersect. And so if you think about like this tissue box in the middle here, all of these planes, these are going to meet each other. These dihedral angles are all going to be 90 degrees because they all meet at 90 degrees. So they have those corners that you're used to when you see a tissue box. There are other dihedral angles though. For example, like let's say if you had this, we'll pretend this is like some sort of tent. You might have a dihedral angle right there of maybe just 30 degrees. And it looks like these might be 30 as well. Or actually that wouldn't work. I should actually say 60 because 60 plus 60 plus 60 is 180, and that would complete the triangle. So let's call those 60 degrees. Or maybe you've been in a room, I can think of a room at WCC, there's a math room, LA, I think it's 262 or something, and the walls are actually they don't all meet at right angles. So there's a couple of walls that actually meet at it's an obtuse dihedral angle because the walls sort of go out, like if you were looking down from the ceiling down to the room, the walls kind of go like this, like it's almost like an octagon shape on the one side of the room. So these would be dihedral angles where those walls come together there. So let's jump back to lines again. So we've got lines in 2D and we talked about parallel versus intersect. Now let's talk about lines in 3-dimensional space. So in 3-dimensional space, we can think of lines Oh, and it looks like my little box here moved down. Let's see if I can move it back. There we go. Okay, so with lines in 3D, we actually have three options. They can be parallel, they can intersect, and they can be what we call skew. So we've got this new relationship that's possible with 3 dimensions. So parallel lines are lines that never touch. So they never touch or intersect. And so an example might be like this line right here is parallel to this one over here. We could also say that they're parallel to this one down here. So there's a couple of different scenarios of lines that are part of this box. They could also intersect. So an option might be this one right here intersects with this one right here. So those meet each other and intersect. Well, the third option, skew, is that those skew lines are not parallel and they don't intersect. So see if you can figure out where on this box might be two lines, use the line segments that make up the box. Where could you find two lines that are not parallel? So parallel meaning like they're not gonna touch, and let me add, never touch and run in the same direction. So find two lines that don't run in the same direction, but they're not going to intersect. One option, okay, and you can pause the video if you want to think about it a little bit more. One option might be this line right here and maybe this one right here. And I know on my paper, it's hard on the paper because it looks like this line is going to intersect this one, but imagine that tissue box. Like imagine this is a tissue box. The top line of the tissue box runs at a different plane than the bottom part of the tissue box. So it actually is not tilted. It's tilted in 2D just to make it look three-dimensional. But if you actually had a tissue box in front of you, you would see that the top part of the tissue box is never going to run into the bottom. And you could also think about the room that you're sitting in. So like look up at the ceiling and maybe think of the line, pick one of the corners of the ceiling and think of the line that runs from one corner to the other, so where the ceiling and the wall meets, and then look down at the floor, maybe in another place where you see a line where the wall and the floor meet, and you could probably find two lines that aren't going in the same direction but are never going to meet because one is against the floor and one is on the ceiling, and so that would be skew. So hopefully that makes some sense. It's definitely easier to explain in person, but definitely let me know if you have questions. So let's talk about the group of shapes that make up those 3D shapes that I was talking about at the beginning. So Polyhedra, that's the name of the group of solid surfaces or 3D shapes that are all made of, where every surface is made of a polygon. So Polyhedra, that's plural. So all of these shapes here are polyhedra. Polyhedron, that's singular. It's a geometric solid, so that just means a 3D shape where all surfaces are made of polygons. So notice like all the sides and the bottom are made of polygons. And remember, a polygon is a closed surface made of line segments. So for example, this would be a polygon. A circle is not a polygon. So a cylinder is not going to be considered a polyhedra. It's a 3D shape, but it's not a polyhedra because it's made up of, it has some circles there. A cone is not going to be a polyhedra. A sphere is not going to be a polyhedra because it's got rounded parts to it. So let's label a polyhedron. So we've got a couple of different parts here, and this is important. So as early as kindergarten, we start having them identify vertices or vertex, and then not so much definitely faces and edges as well, but sometimes we don't necessarily use those exact words. We can just say, sides, like how many sides does this cube have? But by first grade, we're definitely using all of these terms. So vertex is the point where two line segments meet. So this is singular. And then vertices would be plural. So if you want to refer to more than one, you say how many vertices does this have? So there's a vertex. So we've got a vertex. An edge would be the line segment where two sides meet, and then a face would just be the entire side. So in this figure, there are 6 faces. We can count the edges, and I'll use a different color so you can see it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 edges. And then I'll count the vertices. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So 8 vertices. So by first grade, students should be able to identify number of faces, vertices, and edges in a 3D shape. All right, so let's do some examples. So example 1, this is a great place to pause the video and try this on your own. You could try example 1 and 2 actually, and then go ahead and play the video when you're done. So example 1 are the following solids polyhedra. So what we're looking for is a closed, it's got to be closed, so no holes, and we've got to have all the sides are polygons, which basically just means no curves. So anytime you see a curve, like this cone is not going to be a polyhedra, the sphere is not a polyhedra, this one is not a polyhedra because it's got this hole in the middle, but these first two, this would be yes, and this would be yes, because all of the sides of those are polygons. With example 2, it says label the vertices for the octagonal prism below and answer the question. So let's actually label this. I'm going to identify each vertex and I'm going to give it a letter. So I'm going to call this A, B, C, D, E, F, G, H, okay? And then I'm going to go down and I'm going to continue. So I'm going to call this J, K, L, M, N, O, P, oh, did I forget I? So I did. Let's call this one I. There we go. So we've got A, B, C, D, E, F, G, H, and then I, J, K, L, M, N, O, P. Perfect. So we want to label it so we can answer these questions. And if you did this already and you already labeled it differently, that's totally fine. So how many edges does this solid have? So if we go ahead and label them, we can count 1, 2, 3, 4, 5, 6, 7, 8, and it should be the same on the bottom. 9, 10, 11, 12, 13, 14, 15, 16. So it looks like 16. And then how many vertices does it have? It looks like I already identified those. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 vertices. How many faces does this solid have? So with the faces, we're looking at, I'm going to go ahead and erase. Well, actually, I don't necessarily have to erase. I could try to leave that. So for faces, we've got, let me go through the sides first. So we've got 1 face, 2, 3, 4, 5, 6, 7, and then there's this one on the side here, 8. So it's an octagon top and bottom. Let me go ahead and erase it now so we can see a little bit better. Another thing that I could have done is we could do this as 1 face, 2 face, 3, 4, 5, 6, 7, and then 8 back there. That might be a better way. And then we also have the top, so we'll call that 9, and then we have the bottom, which is 10. So there are 10 faces altogether. And then it says name 2 faces that make a right dihedral angle. So I want you to imagine, for instance, for a minute, this is hard to kind of visualize, but I want you to imagine that you've got, this is an octagonal prism, so it's got an octagon top and bottom. And imagine this is standing straight up on the desk. And if it was standing straight up on the desk, that means that each one of these sides is going to form a right angle to the base, to the bases, to the top and the bottom. So there's lots of different possibilities to answer D, but we could name, for one example, would be name the top face and then one of the sides. So this side is going to make a right angle with the top there. So this angle is a right angle, and it also makes a right angle with the bottom, but that's just one example. So how do we name this? Well, we have to go back to our vertices. Probably shouldn't have erased those. C, D, E, F, G, H. And then and OP. Okay, and so we want to name the top face. So remember that when you're naming a face, it's a plane, you need at least 3 points. So I could say plane A, B, C. I could say A, B, C, D, E, F, G, H, or A, B, C, D, E. You know, there's lots of possibilities, but it has to at least have 3. So plane A, B, C, and this side here, we have to name at least 3 of these points. So I could say I, H, G would be fine. And again, that's just one possibility. I could have said G, PI would be another one. As long as you have 3 points that are on the plane, then that works. And again, this isn't the only combination. Any of these sides with the top or the bottom would work for D. And then name 2 faces that make an obtuse dihedral angle. So an obtuse angle is an angle that's greater than 90 degrees. So something like this, an obtuse angle. And imagine for a minute that you're looking down on this shape. So if this shape is an octagon, we've got 1, 2, 3, 4, 5, 6, 7, 8. So imagine that you're looking down like an aerial view on this shape, and all of the sides are going to come together at a dihedral angle. So one possibility might be, and I'm going to go ahead and I'm going to get a different color. You could just name any of the 2 sides. So like you could name this side right here and this side right there. Those meet at a dihedral angle. So it looks like GPO would be this first one on the left, and then it looks like FON. Those would be that would be one example, but again, there's a lot of different possibilities. So if you wrote down any of the 2 sides coming together would be a dihedral angle. And actually, we could go one step further, and I could ask you what dihedral angle would that make, and you could think about that for an octagon. So next, let's talk about convex versus concave. So polyhedra can be convex or concave, and you may have heard these terms. Well, you have heard these terms in terms of 2-dimension, and it's not too different. With convex, you can kind of think of it as not being caved in, like there's no parts that are caved in, whereas concave, we have these caved in parts. So like you can see on this figure that it kind of caves in there. There's that indent, so that's why we call it concave. That's a hard it's a hard way to think of it sometimes, though, depending on the shape. So one thing you could do, and we talked about this with 2-dimensional shapes, is think about, it says if all line segments drawn inside the polyhedra stay inside, then it's convex. So like if you were to imagine a person standing inside this polyhedra, and let's say we've got a person here and a person here, and they held the ends of a string to make a line segment. That line segment would be inside. And you could put people anywhere inside this figure, any 2 people, and that string is going to stay inside. And the second shape, it wouldn't work though. If you put a person here and you put a person here and they held a string, see how that string is outside the figure? So that's why we say it's concave. So go ahead and try example 3. So convex or concave, and this would be a great place to pause the video. So this first one is convex. We don't have any sinking parts. And if you drew a line segment anywhere inside, it would stay inside. This is concave. And if you draw a line segment from this part to this part, it would end up going outside. And then this last one is convex, because to a line segment, any line segment that you could draw on that one would stay inside the figure. So the other part, and this should have been, this moved down a little bit, but polyhedra can be right or oblique. Hopefully on your notes it should be at the top here. So those are 2 other ways that we can describe a polyhedra. So right just means that it's standing straight up. So like this, let's see here. Oh, you know what? I'm wrong. Take that back. This isn't necessarily for the top here, but polyhedra can be right or oblique. It does apply. Let's back up for a minute. I should talk about prism versus pyramid first. Sorry about that. I got ahead of myself. So a prism is a polyhedron with two parallel bases. So for example, right here, these are the bases. They're parallel. This base right here is parallel to this one. Even though it's tilted, they're still parallel. They're running in parallel planes there. And so we call that a prism. So, and they're not necessarily always standing on the base. It's possible that they're standing on one of the other sides. For example, that tent that we saw at the beginning of the notes that looks somewhat like this. The bases are here and here because they're parallel. Bases always come in pairs. So the bases are the triangles and then the sides are the rectangles. And a prism can either be right or oblique. Right meaning it's standing straight up. So this one is right and this one is tilted. So oblique just means that it's tilted. And you can see here, that should go down there. So right or oblique, you got the definitions there. And then a pyramid is just, I'm sure you know what a pyramid is, but the one thing that I want to make sure that it makes sense here is that a pyramid doesn't necessarily have to have a square base. So if you think of like the pyramids in Egypt, for example, they all have square bases. A pyramid doesn't have to have a square base. So this is what we call a triangular pyramid. And it's standing straight up, so we call this a right triangular pyramid. This is what we call, it looks like a square. We could call it a rectangular pyramid if we weren't sure if the base is a square. So we would call this an oblique because it's tilted, square pyramid. So as long as there's one base, okay, one base, so we call these the bases, and then they all go up to a point, which we call an apex, then we call that a pyramid. And then just to back up, let's name, I'm going to name these ones so you have these in your notes too. So with this prism, we always name the prism based on the bases. So if the base is in this one, let me just erase this so we can see it. So ask yourself, what shape is this base? It looks like a trapezoid to me. So, and if you weren't sure, you could even say it's a quadrilateral prism, but to me this looks like a trapezoid. Remember, a trapezoid has two parallel, looks like this one might be parallel to that. So two parallel sides and then the other two sides are not parallel. So we're going to call this a right trapezoidal prism. And again, if you could also call it a right quadrilateral prism. Quadrilateral means four sides if you weren't sure if it was a trapezoid, because sometimes these are hard to tell. And then the second one, it's oblique, and then it looks like there's 1, 2, 3, 4, 5. So it's a pentagon. So a pentagonal prism. So an oblique pentagonal prism. So I did put a note here. Sometimes it's hard to tell if it's tilted because these are all drawn in 2 dimensions. Like I'm just thinking of this one right here. It's kind of hard to tell. I would say just do your best guess. Do your best guess with homework and the exams. And I'm never going to take off points if you make a guess and it looks like and it's really hard to tell. And hopefully you'll have some good examples where you won't they won't be too ambiguous. So for example 4, this is a great place to pause the video and try these on your own. So I want you to name the polyhedra. I want you to tell me, is it right or oblique? So right or oblique. And again, just make your best guess. And then you're going to tell me the name of the base. And then is it a prism or a pyramid? And you're going to put that all together. So for example, the first one, the base, this looks right to me. It looks like it's standing straight up. So I'm going to say right. And the base is a triangle. So triangular. And remember, the bases always come in pairs. So if you're wondering which two sides are the bases, they're not always necessarily going to be shaded. So look for the shapes that come in pairs, parallel pairs. So right triangular, and this is a prism because there's 2 bases and the one base doesn't go to a point. So right triangular prism. This would be a great place. Pause the video and try the other ones on your own. So this second one looks a little tilted to me, so I'm going to call it oblique. So oblique, and we're going to look on the bottom. It looks like I've got 1, 2, 3, 4, 5, 6. So a hexagon. So we call it oblique hexagonal or hexagonal. Oblique hexagonal, and then it's a pyramid. Okay, this next one looks like I've got a right, looks like it's standing straight up. So right rectangular, since the base is a rectangle, rectangular, and then prism. This one I've got a base of a 5-side, so pentagon. And it looks like it's standing straight up. This one's a little hard to tell, but I think it's standing straight up. So I'm going to call it a right pentagonal prism, not prism, pyramid. Okay, and then this one we've got 1, 2, 3, 4, 5, 6. So that's a hexagon. So hexagonal. It looks like it's standing straight up to me, so I'm going to call it a right hexagonal prism. And then last, we've got looks like a square base. If you're not sure, you can call it a rectangle, which is fine, because remember, all squares are rectangles anyway, so you can't go wrong there. So I'm just going to write down square, and then it looks like this is tilted, so I'm going to say oblique. But again, if it's hard to tell, you could probably argue right, but it looks tilted to me. So oblique, square, and then pyramid. Awesome. So if you can get your hands on actual 3D figures, or even just pay attention as you're going around your house, you know, and see if you can find these in everyday life, because, you know, they definitely show up. I mean, not so much maybe the hexagonal pyramids and those kinds, but definitely the prisms, definitely the, you know, rectangular prisms, and then, we'll talk about some rounded ones in a minute, and you'll find lots of good examples for those around your house too. So this next section, I want to mention the 5 Platonic solids. These are kind of fun to play around with. I actually have a couple sets of these for the classroom. So if we were actually in person, we would play around with these. What's nice though is I actually found a really cool site, and the link is here. I encourage you to click on that. And the nice thing about this site is it's actually, it shows you, and I'll just show you what it looks like. So you can click on, so when you click on the site, you've got to scroll down a little bit, and then the 5 Platonic solids are here, and you can just click on them, and it shows you the Platonic solid being rotated, which is nice. But then it also shows you, it's called the net, with what you would get if you took this Platonic solid apart. And this is a nice way to look at the shape. So even if we were in class right now, we wouldn't have that net to look at. So this is kind of a nice website. So I'm going to go back to our notes, and let's back up, and I'll talk about what the Platonic solids are. So they're a very special type of polyhedra where every face is formed by a regular polygon. And remember from past sections, last section, a regular polygon is just a polygon where all the angles and sides are congruent. So let me see if I can get hang on a minute, my pen needed to reboot here. Okay, so regular just means congruent sides and angles. Okay, they're considered regular polyhedra. So just like a regular hexagon might look like this. So 1, 2, 3, 4, 5, 6. That's where all the sides are the same, and all the angles are the exact same. A regular polyhedra would be if you have that 3-dimensional version of that. There's only 5 of them though, and they have these special names. So we're all familiar with cube, but there's some of these other ones that we might not be as familiar with. So what I'd like you to do now is pause the video. You're going to go to this site, and I want you to try to fill in this table: number of faces, number of vertices, number of edges for all of the Platonic solids. And then the faces plus vertices, you'll do that at the end. You'll just add these 2 columns together. So for instance, like the cube, you're going to go to the website and you're going to count. We'll click on cube and we'll count the number of faces. So it's really easy to see on this because it's laid out. So 1, 2, 3, 4, 5, 6, and then you're going to count the edges. Now with the edges, be careful, because with the net, you don't want to count them twice. So for instance, like if this side is flipped up, this edge right here meets this one, so that those are really the same edge. So you might want to think of the actual 3D version of that. And you can even click on number of edges here, and it will highlight the edges for you, or click on vertices, and then you could click on faces too. So try that, pause the video, try that, and see if you can fill in this table. And I think you'll find that there's something special, a relationship between these parts that occurs with the polyhedra. So I'm going to go ahead and just fill in the table. Hopefully you've gone through and tried to do this yourself. So with a cube, there are 6 faces with a cube. There are 8 vertices, and there are 12 edges. And if we add 6 and 8 together, we get 14. With an octahedron, there are 8 faces, there are 6 vertices, and there are 12 edges. And if I add 8 and 6, again, I get 14. With a tetrahedron, there are 4 faces, so that's this one right here. There are 4 faces, there are 4 vertices, and there are 6 edges. And then if I add 4 plus 4 is 8. An isosahedron, there are 20. This one's hard to visualize. 20 faces. It's nice at least to have the net for that one. And then for vertices, there are 12 vertices, and there are 30 edges. And then if I add 30 and 12, I get 32. And then dodecahedron, there are 12 faces and 20 vertices, and there are 30 edges. And so if I add 12 plus 20, I end up getting 32. And so what I want you to do is look at the faces plus vertices column and then the edges and compare the two. So 14, how does that compare to 12? 14 compared to 12, 8 compared to 6, 32 compared to 30, 32 compared to 30. And what happens is you can see this relationship here that if you take the faces plus vertices, so faces plus vertices, it's the same thing as the number of edges plus 2. So for example, 14 is equal to 12 plus 2. 8 is equal to 6 plus 2. 32 is equal to 30 plus 2. And so there's a special relationship that happens, and it's called Euler's formula. So Euler is a mathematician, a famous mathematician, and he discovered this relationship and this formula. So Euler's formula says that the faces plus the vertices are equal to the edges plus 2. Okay, so it's just kind of a fun relationship. And sometimes there are other polyhedra that have a similar relationship with this, and you'll see that in the homework. There's a problem or two where it asks you to kind of look at this relationship a little bit further with other types of shapes. So just playing off of the Platonic solids, just like semi-regular tessellations, remember those were tessellations where maybe we had more than one shape combined to tile a floor. We can also have a semi-regular polyhedron, and a semi-regular polyhedron is just a polyhedron that has more than one regular polygon together. So think of like a soccer ball, for instance. So for a soccer ball, you've got a pentagon, and then you've got 1, 2, 3, 4, 5, 6. So you've got pentagon and hexagons together. Or this shape, it looks like we've got a pentagon and then a square together. So if you have more than one regular polygon to make that 3D figure. And then the last part, we're just going to talk about some curved shapes in 3D because we haven't talked about anything curved yet. So the curved shape would be the cylinder, the cone, and then the sphere. So a cylinder is just 2 parallel circular bases. Now I put this definition, this is the one the book uses. Technically, like if you Google the definition of a cylinder, you'll find a couple of different definitions out there. Most of them say circular. There are definitely definitions though that say any curved base. So for instance, like, you could make some shape like this, and if I shouldn't have made it that complicated, and think of like the same shape top and bottom and then connected it like that. Connected the sides, and that could be considered a cylinder too. In terms of elementary school though, usually we just stick with the circular bases. It could be right or oblique, just like the pyramids and prisms. So oblique just means it's tilted, right just means it stands straight up. A cone, so a circular base that comes to this vertex, which we call an apex, and that's the same word that we use for the pyramid, the point on the pyramid too. So, and you can have a right and oblique cone just like you can a cylinder. And then lastly, I'm sure we all know what a sphere is. A sphere is just, we know that a sphere looks like a ball, but let's look at the definition. So a sphere is the set of points in space in 3 dimensions that are a fixed distance from the center. So imagine the very center of a ball. Okay, and imagine that you're actually holding a real ball in your hand. It'll be easier to think about. So imagine the very center of a ball, like a baseball, and then imagine all of the points around it in all of the different directions. If you were to connect that center with all of the different points at a fixed distance around it in 3D space, then that's how we create this sphere. And I put a little note here. How is the definition of a sphere different from a circle? Because if we think about a circle, so if we have a circle has a center as well. And the definition of a circle is when you have a set of points that are at this fixed distance away from the center, and if you keep connecting it, you end up getting this circle. So it's very similar to the definition of a sphere, but we have to have some difference here. Otherwise, we're going to get the same thing. So sphere is not the same thing as circle. So the difference here is that a circle is the set of points in 2 dimensions that are a fixed distance from the center. So small part of the definition, but really important. So 3D versus 2D is going to differentiate between a circle and a sphere. So that is it for 10.3. If you have any questions, just let me know.